Good afternoon to all from the editorial board of BuildUp Portal. Sorry we're a bit late today, but let's move on. For the ones who are attending a BuildUp webinar for the first time, welcome. For our returning audience, thank you for renovating your interest. So just a brief explanation of what is BuildUp. BuildUp is an European collaborative platform in the field of energy efficiency in buildings. It is continuously updated and it represents one of the key sources of information on the topic of energy efficiency. You can register and become a member of the community, and you can also upload news, events, present case studies, results from projects, and so on. I would like to invite you all to navigate the portal. In the Learn section, you will find all the podcast of the past webinars, so it is possible to listen to all the previous presentation. At the end of this webinar, the link to the video registration and the file to the PDF presentations will be made available in this section of the portal. So it is a pleasure to host today's 10th webinar of the EPB Standards series entitled Example Calculation with a Set of EPB Standards, Focus on Residential Buildings, Energy Needs Combined with Specific Systems, which is organized in collaboration with the EPB Center and REVA, the Federation of European Heating, Ventilation and Air Conditioning Associations. So this webinar concludes the second edition of the EPB series of webinars. I would like to invite you all to contribute and participate in this webinar. You can ask questions by typing in the box on the right side of the screen. They will be answered at the end after the presentation in the Q&A session. Now I would like to present the agenda of today's webinar and introduce the panelists. First, Jaap Hogeling, Chairperson CNTC 371 from the Energy Performance of Building Project Group, European Committee for Standardization, will do a brief introduction. Then Dick van Dijk, EPB expert from the EPB Center, will present specific features of the calculation of energy needs for heating and cooling for non-residential buildings. Then Gerard Zweifel, EPB expert and Professor Emeritus at the Lucerne University of Applied Sciences and Arts, will discuss the integrated application of the EPB standards on energy needs, ventilation and air heating and cooling with demonstrations. And last but not least, Laurent Sokal, independent EPB expert, will present the modular approach from component to overall energy performance. Now I would like to leave the floor to Jaap, and please we can start the session.
Thank you, Julia, for your introduction. I'm Jaap Hogeling, and I'm just giving a short introduction to this 10th webinar. My background is I was involved in the development of the set of EPBD standards, and through the EPD Center also on the actions to disseminate all information around the set of EPBD standards. The goal of the example calculations, which is the subject of our series of webinars, is to show, demonstrate the functionality and to show that the calculation works with practical cases, and to demonstrate the available features to describe the energy performance of buildings and the HVAC installations. Also to show the sensitivity of the calculation procedures, what is the impact of single data or groups of data on the selected calculation results, and to demonstrate the usability, the data input, avoiding complexity of data input, and the description of practical system configurations, and by showing useful results. We do this, and we did this for individual calculation modules and for the whole building calculation procedure. As said before, the three experts from the EPB Center will present on the overarching standard in ISO 16-1. Dick van Dijk will show that this standard is suited for residential and non-residential buildings. Later, Gerrit Zwijvel will demonstrate the integrated application of the energy performance of building standards on energy needs, ventilation, and air heating and cooling systems. And finally, Laurent Sokal will illustrate the modular approach from component to overall energy performance. The energy performance calculation standards are great tools. The presentations will and did demonstrate that using hourly calculation methods correctly, you can extract a lot of useful information to decide on the best building and system design by comparing different possible solutions. So they can help you as designer also to guide you in the right direction. Thank you very much, and the next speaker will be Dick van Dijk. Thank you.
Thank you, Jaap, for your introduction. So my presentation will indeed be on the EN ISO 52016 Part 1. That's the calculation of energy needs for heating and cooling. And in this case, I'll focus a little bit on non-residential buildings. Jaap said that this is the overarching standard. Well, it is one of the core standards, but as you all know, the overarching standard is the EN ISO 52000 Part 1. Let me quickly move on. So my background, I'll skip this one because you can read it later on in the recording of this webinar, if you're interested, of course. So the EPB standard EN ISO 52016 Part 1, heating and cooling needs, and also indoor temperature calculations. So there were some questions on this standard. For instance, is it only suited for residential buildings? Well, the answer is no, it's not. It's also for non-residential buildings. And what can the demo spreadsheet be used for that I introduced also in the previous presentations of this series of webinars? So this means that I'll try to explain in, well, only 10 minutes, the basics of the hourly calculation method in this standard, some main features of the spreadsheet with some illustrations this time, illustrate also how different climates and use patterns can be applied in this spreadsheet, and new developments in the spreadsheet, and something on the link with the systems. So just to recall, because if you have attended previous webinars, you've seen this picture already a few times. The standard to calculate the energy needs for heating and cooling contains both an hourly calculation method and a monthly calculation method. And they all both use the same input data and boundary conditions. Of course, the monthly method uses our monthly average values, and the hourly method uses the pure hourly values. And of course, the hourly calculation method can also give you the hourly indoor temperatures and heating and cooling loads, and the monthly method gives you only monthly results. But they run in parallel in this standard. And an extra feature of the hourly calculation method is that it provides you as extra output the monthly characteristics, which in turn can be used as a basis to generate or validate the correlation factors which you need for the monthly method to take into account the dynamic effects like internal gains and solar gains and so on. If you're more interested in more details on the hourly versus monthly calculations, then you can look up the recording of the 4th webinar from last year. So the hourly calculation method in this standard is actually quite similar to a building simulation tool. You calculate the overall energy balance each hour, and I apologize for the typos in this presentation. I'll skip this one and go to the next one because I want to illustrate the model that is used in this standard for this calculation. It makes use of the so-called resistance capacitance model, which means that each construction element is divided into a number of nodes and a number of layers. And in each thermal zone, you'll have a number of construction elements, and each construction element has a number of nodes. And you have the indoor air node, and you solve the heat balance each hour for all these nodes, which means M times N interrelated energy balance equations that are solved to obtain the temperatures at all nodes and the heating and cooling loads. Well, this part of the spreadsheet, if I come to the spreadsheet, is done by a macro, because if you want to solve this in the spreadsheet itself, then it takes too much time for calculation. So this is the only part which is done at the background in the spreadsheet, because before I forget to tell you this when we come to the spreadsheet later. Well, so this is the set of equations in the standard, and there are also alternative equivalent models allowed to calculate the dynamic energy balance for each hour. And so looking at the illustration, so here you see the construction element divided into 4 layers. Each layer has a thermal resistance, each node between the layers has a thermal capacitance, and you have solar radiation, which is absorbed in each node, of course, only if you have a transparent layer which passes on the solar radiation to that node. But of course, you have solar radiation incident on the outdoor surface, and you have thermal radiation to the sky, you have the outdoor temperature, and at the inside you have the indoor temperature, and you might have solar radiation on the indoor surface, which comes via another opposite window, for instance. Well, so this is for each construction element, a little bit simpler and different for window elements. And then all these elements are in a thermal zone, and they interact in the thermal zone with the air and with each other by thermal radiation and so on. So I'll not go into the details of this. This was just to illustrate that this is similar to a building simulation tool, and then you can have multiple thermal zones, and you have national rules, for instance, to determine these zones. Yeah, so as I said, alternative modeling is allowed, and all these options that you can choose, for instance, at the national level, they are, as you know, if you have attended previous webinars, they are all given in normative Annex A. So here you find, for instance, table A10, which can be filled in at national level, whether or not to allow for an alternative method, and if so, to give the reference to that method. Well, so that's the similarity with most building simulation tools. The difference is that this model is tailored to the needs, and the needs is assessing the energy performance, which implies that we took care that no more input data is needed from the user than you would need for the monthly method. And then in addition to that, you will have hourly climatic data, and you have internal heat gains and so on with hourly patterns. But these are supplied at the national, regional, or regional level to have standard conditions for the calculation. And the model is simplified where this is possible. And the model is fully transparent and unambiguous, so all the equations are spelled out, all the results are traceable, which means that you can also easily add or expand the model with innovative technologies. And it's part of the modular setup of all EPB standards, which means that the input and output is clear and linked to other standards. So you can also check the interconnectivity with other modules. So now it's about time to show something on the spreadsheet. Yeah, I've said it before at previous webinars, but it's important to repeat that the spreadsheets were made to demonstrate and validate the standards. So the highest priority is to make these spreadsheets technically correct and transparent. So where possible, all the intermediate results are shown, and at each step of the calculation, references are given to the corresponding clause or formula in the standard. And you have a clear input and output, so you can show the interconnections with other standards. So this, at the same time, creates some limitations to this spreadsheet. So limitation is that they are not intended for daily practice because they are not so user-friendly, and the performance might not be usable for daily practice. There are also some practical limitations on the choice of the input data, and some special features may not be included in the spreadsheets. So the demo spreadsheet on this standard can be found at the website. You can look up this information. And yes, there is an update in preparation. I'll tell you more about that later. So let's go to a sheet where you find the input for each construction element. So what you find here, what you have to fill in, is the description and the type of the element, the class, which means the composition of the element, U value or thermal resistance, capacity, area, solar absorbance at external surface, G value if it's a window, orientation and tilt. Well, in short, the usual input data, which is similar for simplified methods. So this is the input for both the hourly and the monthly method. And then you have a sheet with other static input, so time invariable input like area, volume, thermal capacity, temperature set points, humidity set points, internal heat gains, airflow range if it's not an input from the ventilation standards, correlation factors for monthly method, and again, the usual input data. I'll try to click to the next slide, but that doesn't. Yeah, it worked. So let me zoom into the set points and schedules. So at the moment in the spreadsheet sheet, we created 3 levels. So level 2, high comfort required, level 1, moderate comfort required, and low comfort required is level 0. So we use that for the set points for heating and cooling. But that's also something, the 3 levels can be used for internal heat flow, so constant internal heat flow, and then extra internal heat flow during moderate comfort hours and during high comfort hours. And also for humidity, you have the set points in it, and for moisture production inside the thermal zone, you could have difference between different types of hours. Well, and what are these hours? Then you come to the other sheet with the use patterns, which gives you the weekly schedules. So for each hour per day, and with a distinction between weekday and the weekend, you have occupancy levels, 1, 0, or 2, and you have comfort levels. And so the occupancy level are used for internal gains and the moisture gains, and then the comfort levels used for the temperature and ventilation set points. And then we added also operation of systems if you want to make the link to the systems, but these are not used in the standard mode of the spreadsheet. So you could also have 3 levels of operation. And you see here these banners. These are just some examples. So if you want to see the full details, then you go to and download the spreadsheet. And of course, if you have questions, just fill in the contact form at the website and we'll try to answer your questions on this. Then you have a sheet with hourly input. And here you see all these levels coming back for each hour of the year, for the full year, and ventilation, internal heat, temperature set points, and so on. So yeah, but this is not as flexible as the standard allows, because the standard allows you any data for any hour in the year. So what we have in preparation now is to replace this schedule by hourly input for a full year generated by a use profile generator. And this use profile generator has been developed by Mr. Laurent Socal. And the profiles are based on EN 16798 Part 1. That's another EPB standard which deals with the indoor environment requirements. And what you can find in this use profile generator are use profiles for different building categories. For instance, for a detached house, here you find the occupancy, the heat from appliances, lighting, etc. And you can choose this one, or you can have a customized data set built in this one. And you have CO2 production, temperature settings, ventilation rate, CO2, humidity, lighting, etc. But also domestic hot water, so the profiles and the temperature of the domestic hot water. And then you press the button to generate hourly values, and you get for the full year hourly values for the heat gain from appliances, persons, vapor, CO2, temperature set points, etc. And what is now a work in progress is to combine these data, for instance, the heat gains from appliances and from persons. You can combine that into total internal heat gains to make these data fit as an hourly input for a specific EPB standard, for instance, the EN ISO 5216 Part 1. And then you have a very flexible way to have the hourly use profiles in that standard. Yeah, and another feature you can then create is that you can replace the set points for the temperature, which are fixed for a certain time of the day, into adaptive temperature set points, again based on the same standard or customized. For instance, you have national annexes in Switzerland and Denmark who replace these default adaptive temperature set points by a modified version of that. Yeah, so that's also something which is in preparation to use, and that's specifically for residential buildings and offices without mechanical cooling. So going back to the sheet with the hourly input data, you also can use these hourly data to, for instance, to change the fixed properties of windows into variable properties of windows, in this case, movable solar shading devices. In the next version of spreadsheet, this will be made a little bit more user-friendly and flexible. And it also allows you to make the connection to the ventilation standard, so you can have variable ventilation properties as an hourly input and link with the system. So for instance, like I showed at the previous webinar, a variable maximum system power, the heat pump system in the previous webinar, can be brought in here as a hourly variable input. Then we have another sheet with the hourly climatic data, and the nice thing of this one is that it's just, you can simply copy it from the output of the spreadsheet on the standard on climatic data, the standards, this one, the conversion of solar radiation from horizontal to any other orientation and tilt. And this gives you the hourly values for all the climatic data that you need. And then you have the sheet with hourly output data. Again, just some examples of it. So the internal gains, incident solar radiation of each construction element. So these are typical intermediate results that you can check. And the calculated energy needs and the indoor temperatures. So the air temperature and the mean radiant temperature, and from that, the operative temperature. Or the moisture properties that you have calculated, again, for each hour for the full year. Then we have the sheet with monthly output, which is a summary of all the hourly output then per month, but also statistics. So for instance, statistics is the heating load distribution for each month in fraction of maximum power, and the number of hours per month with the operative temperature exceeding a specific limit, in this case set to 20 degrees, but that you can change this number. So that's derived from the hourly output data. But you also have a sheet which does the calculation for the monthly method. So the monthly method gives you the monthly calculation and the output for this calculation. So you see here just an extract from that. The heating needs, if there's no intermittency, time constant, solar and sky radiation, so all the monthly values, the heat losses, the gains, the balance ratio, and intermittency correction factors. Then finally you have sheet with graphical output. Just show some examples of earlier presentations. So examples of hourly data, the energy needs, where you can directly compare the monthly method, here the heating needs and the cooling needs, with the hourly method. But also the heating load distribution curve for specific months, or the time weighted temperature exceeding 26 degrees for each month. And that brings me to the conclusion, but because I see time is running, that in ISO 52016 on this standard, I hope that I have been able in this very short time to illustrate a little bit that the hourly calculation method is pure physics and it's purely dynamic. So in this sense, it's fully comparable with building simulation tools, but it's tailored to the needs. No more input for the user than the monthly method. It's fully traceable. It's fit for various climates and use patterns, both residential and non-residential buildings. I also try to illustrate briefly that the spreadsheet features and further developments for demonstration and testing, that they are transparent, also in interconnection between these standards. I guess I hear Gerhard in the meantime already preparing for his presentation. So I'll conclude with the monthly method. I said not so much about the monthly method. It's also an option in the standard. That's what I told, but it requires extra care because you have to come up with the correlation factors to take into account the dynamics. But I'll stop here with my presentation, and I like to give the floor to Gerhard Zweifel for his presentation.
Thank you, Dick. I hope I can be heard.
Yes.
So I'm going to show you an application of three different spreadsheets with three different standards in the area of the energy needs, the ventilation, providing heating and cooling. I'm skipping that background slide as well, so you can read about my background later on if you want. The involved standards of the example that I'm showing are those three. Is just the one that Dick was talking about before. And then we have EN 16798-7, which is actually the standard on the determination of airflow rates. And we have 16798-5-1, which calculates distribution and generation of ventilation system. When we talk about generation, we mean the air handling unit, but I'm going to show that later on. The spreadsheets of all three standards, of course, can be found on the EPB Center homepage, but all of them have been updated for this case study. So there have been done some little changes to make this connection possible. Why do we couple those different spreadsheets? Well, the following is path is actually what we try to do. We try to calculate with EN ISO 52016 the calculation of the required heating and cooling needs, and also the calculation of the room temperatures, be it air or operative temperatures for the use here. The air temperature is the important one. But these are calculated based on really supplied and extracted heating cooling energy. Then 16798-7 calculates the required airflow rates and or the supply air temperatures for mechanical ventilation. So some of you may have seen a webinar on the same standard actually dealing with natural ventilation. This standard actually covers both mechanical and natural ventilation in respect of the calculation of the airflow rates. So it for the mechanical ventilation actually transforms the energy needs from the former standard into flow rates or into supply temperatures, depending on the type of control that we choose. I'm coming back to that. And then finally, EN 16798-51 calculates the airflow rates and the air temperatures really supplied for this mechanical ventilation based on the required flow rates and or supply temperatures that the previous standard has calculated. And what we show here actually is also the effect of limited capacities or of operational deviations from the actual needs. The relevant content of 16798-7 is, what we try to cover here is what we call the emission module in the area of ventilation. That means the flow rates, or here for mechanical ventilation also the required supply temperatures to fulfill either the indoor air requirements based on 16798-1. We just heard about that standard as well from Dick, or to cover the energy needs, what we are doing here. Technically spoken, actually, it's like equivalent to air terminal devices like VAV boxes, or maybe to nothing, just a calculation-based transformation of values. Then the EN 16798-51 is quite a comprehensive standard covering a whole air handling unit and distribution system. I mean the duct system, featuring all those aspects that are listed here. Control types, heat recovery, recirculation, fan control. There is also an option for ground preheating or cooling. There is humidification, dehumidification, and an option for adiabatic cooling. Maybe it's not even all that is listed here. It's quite comprehensive. This is like a scheme which is found in the standard actually, with a legend associated to it for what is meant by those different stages and so forth. I'm not going into detail, but this scheme is also used in the spreadsheet, and the spreadsheet is, as I said, very comprehensive. It has more than 150 equations, a huge number of options, and an even bigger number of combinations of options. And you have to characterize the components, of course, and so forth. So that having that type of spreadsheet, you actually will notice that there is a need for a user-friendly interface. Otherwise, it's not really usable. So what we have done is adding this type of system configuration sheet in the spreadsheet, where you have drop-down menus for all the different options, so you can easily select from one of the options that is offered, and that makes the use of that spreadsheet quite easier. So how is the coupling of the three spreadsheets working? We have this trio here, starting with the building energy needs. This calculates, as we saw, the indoor temperature and also some climatic parameters, but that's only to make sure that we all three use the same climatic data. So it's not really required that we transport that, but if you make sure that all read from the same climatic file, but it's the easiest way to just put it around. And the indoor air temperature and the required energy need for heating and cooling, that's given to EN 16798-7. This one calculates then the required supply temperature or the required volume flow rate, depending on the setting. We'll just see later what we did in this exercise, and also a system operation signal to 16798.51. And this actually calculates the actual volume flow rate, the actual supply air temperature, and, well, as a consequence, the supplied or extracted energy. What we need to input here is that control signal. When is the system running? Actually, that's given over here. And here we have to put in some control options and design settings, defining how the system is running. Now, what we see is that this goes actually around in a circle, and that means, in fact, that you would have to iterate between the three. In order to avoid that for the case study that I'm presenting here, we actually took those data here from the previous time step, so you can avoid actually this iteration. It provides some other minor problems as well by doing that, but it's working at least without any very time-consuming iteration. As an output from the whole thing, actually, to be processed further by other modules is actually the heating and cooling coil input and output here from the air handling unit. That's the interface actually to other modules like the heating and cooling distribution modules, or even I should actually read 3.1 and 4.1 because those general parts of the heating and cooling should most probably take up this information. So the example calculations that I did with this combination is a pretty simple one actually from the point of view of the building. I took just a 150 square meter landscape office, a single space with the climate of Strasbourg. I just always looked at 2 periods, 3 weeks in summer, in August, and 3 weeks in January, February, and always looked at the last of the 3 weeks in order to have some warm up or cool up periods before. Now, in respect of the ventilation system, I considered 2 cases. One is a variable volume system where the volume flow rate is controlled according to the energy needs. And the supply temperature is predefined in form of it's not constant, but it's predefined in form of an outdoor dependent curve. The other case is a 2-stage ventilation system. It's just 2 different flow rates that it can run, which is predefined. It can be controlled as well, for instance, according to outdoor air requirements. And the control thing is the supply temperature according to the energy needs. Well, I have to note here that the load-based control of both is actually what you could call bad control. There is a way out. If you do it clearly sequentially, then it should be possible. But it's not possible with the current EN 16798.51 standard and spreadsheet. So this is for the summer period the result of case 1. So this is the variable volume system. And what we see here is actually at first we have the room air temperature that's taken from the building energy needs calculation, which is, as we see here, below the set point. The set point is 26, but that's for the operational temperature. So it's the air temperature has to be below because the energy extraction is done purely convectively. So you have to have a lower air temperature in order to take out the energy. Then what we see here is the supply temperature, which is preset, outdoor dependent, and with limits. It's limited to something like 17 and something degrees here. Doesn't go below that. And then what we see here is the dark blue line, the required cooling power from the building, actually, which is transformed to required volume flow rates. And these are actually quite high up here, as you can see. The interesting thing is actually they are higher on cooler days than on the really hot day where we have above 30 degrees peak. And the reason is that green supply temperature curve, which doesn't go as low as on this hot day, actually, because it's outdoor temperature dependent. And now we limit, actually, we don't follow this required flow rate, volume flow rate. It's limited to what the system can provide. So it's limited here to these 1200 and something. And that finally leads actually to loads from the building that are not met. We are actually lower than would be required. And that finally would result in some temperatures that would not be on the set point. Finally here in this week, I show also actually the output, which is the cooling coil power. We have a sign change here in the system. It's not negative, it's positively, and it's pretty different from what the zone needs. And well, some reasons for that are well, the air treatment. There is actually outdoor air has to be treated in order to provide the supply temperature, and there is also some dehumidification, because that's the cooling case. Some dehumidification involved, be it controlled or not. This dehumidification occurs anyway when you have low coil temperatures, and that's calculated as well. Looking at the winter case, it looks pretty similar. We also have now the room air temperatures above the set point because we want to put in heat with the air. We have also some required heating power, which leads to very high required flow rates. The supply temperature again is limited, is following some curve, outdoor temperature dependent. Then we have limited flow rates again here, which again leads to some loads that are not met. We have, especially here on Monday morning, actually there's quite a high peak which is required, which is not covered. That leads to the fact that there will be a few hours in the morning on Monday morning that the set point in the room cannot be met. And again, the output is the heating coil power, which here is much more similar to the zone need. The reason is we do not have some moisture influence, and the other thing is we have a heat recovery, which brings it much closer to the building needs. When you look at case 2, that's now a pretty different thing. We have now a predefined 2-stage volume flow rate, we have now the required supply temperatures here that actually would go pretty low as a consequence of the building energy needs. But we do not follow those required supply temperatures. They are limited here to some 17 something degrees, and again that leads to the fact that the loads are not met. It's a different setting. It's just vice versa. The volume flow rates are preset and the supply temperature is controlled. Similar in the winter case, here we have pretty high peaks for the required supply air temperatures, which are not actually followed because the system is not able to provide those peaks. So it's limited to this value, and the loads as a consequence are not met. That doesn't mean it's always the case. It depends on how you design and dimension your system. I just wanted to show all the possible consequences that the spreadsheets, that this combination of spreadsheets is able to show these effects. So as a conclusion and outlook, while the first sentence Dick has already said, the coupling now shows the correct function of the chain of those three standards for ventilation-based space conditioning. We have looked at two different operational design and control options: preset supply air temperature with load control of volume flow, and vice versa. Further aspects have not been analyzed in the results that I have shown you now, but they are partly included. For instance, the humidification. It is occurring. There is even a set point for the maximum humidity that I didn't touch. I just let it run in the example. This could be analyzed as well, how this influences the whole thing. That actually ends my presentation, and I thank you for your attention.
Okay, thank you, Gerhard, for your contribution. And I will have a couple of words about something that may have worried people. The fact that it looks, all these things look a little bit complicated. So just skip on my background and have a look at the reasons for the fact that it looks complicated, and just say why actually this is not the case. So very often we have to balance between alternatives of different requirements. I mean, for example, the foundation of our life quality is the availability of large amounts of cheap energy. But of course, now the consequences of such a huge energy use is a concern. And we will all sorts of comfort services in a NZEB. In fact, it is a modern building with cooling, ventilation, air conditioning, any lighting, all these things. But we want to use as little as possible resources to get this result. And now if we come, for example, to this EN standard, or in general, the standards that you have for legal requirements, we want to prove that new design buildings will require few resources for standard use, and also we want to display this for any existing building, to put this information on the market, which is the base of an energy performance certificate. And maybe we want to do this calculation before and after a renovation of the same building. So we need to calculate the so-called energy performance of all sorts of buildings and systems, new, existing. For all European climates, we will change the relevance of heating or cooling, or you need both, which is mostly the case when you go to high performance buildings. But we want to keep it as simple as possible. So again, we have to balance. And as it was said in the introduction of this webinar, calculation method we want that is functional, so it works with all types of building and systems, and also it's sensitive, so it reacts to all the available options and differences between systems, between building types, between materials, and encompasses both new and old technology, because we have to compare before and after, and to support a correct renovation evaluation. Then it has to be usable, so it shall have a clear data input, it shall be easily adaptable to context, provide suitable results for its scope, and the scope is double, because you have, of course, compliance with requirements, and I mean the fact that we require a minimum energy performance usually to issue a building permit and then to display this energy performance. And it would be nice, for example, also that the same tool, since we have requirements on energy performance, the energy performance is a design requirement. So if it is useful for this and you use the same tool both for design and for the energy performance, for legal purpose, this would be a big advantage. So you need something that is comprehensive, traceable, realistic, adaptable, but then you want also it to be simple, short, compact, easy to read, and software proof, because most of the difficulties of the complications that might have appeared from our presentation is because we are going into the details of what I will call then later in this presentation the back office. Actually, the front office, that's the user of the standard that will do the calculation of the building, will not see all these details. And you have also a first example just before in the presentation from Gerhard, when you see that all this selection to configure, actually to describe your air handling unit, is just some drop-down menus that will activate the correct calculation sequence. So how can we do to have to cover complex systems with simple items? Usually use modularity. Well, it's quite simple to say. You combine simple items to build or describe a complex system. And for example, in webinar 7, you have this sequence. We start from the needs, then we have systems, and we deal with generations, and we weigh the energy carriers. If you want to have it modular, you make this in pieces, and probably, for example, systems, you will have different pieces for different services, and in system you will have emission, distribution, generation, storage, and you deal with all these individually. And there are several ways to break up this into pieces and to explode in each step in a number of modules. So you go from system to subsystem, and for generation, the different type of generation technology, I mean boiler, heat pump, solar, and then you repeat for all services, and not to mention the building and also the other topics to be touched. And an overview of all modules was given in webinar 2. I think you remember this picture and showing the whole piece of things to be brought together. And which modularity? So when is modularity an advantage? Is when modules have similar properties and internal organization. So if you understand properly one module, probably you nearly know all of them. And another advantage is, since we are in a European scheme, it will take time to converge. So you can easily replace one module with another one, because for another type of generator, or default special module because you want to have a national option or something like this. And don't forget, we have CEN-TS 16629, the detailed technical rules, which specify the common properties of all these modules that have been produced. And which are the common properties of EN EPB modules? In short, first of all, of course, the organization of the contents of the standard and the related technical report explaining what's the contents of the standard, the Annex A, Annex B mechanism to provide national options, and quite important, the structure of the input data, because the big issue when you are in the front end, so trying to use a standard, is really inputting the data. And typically you will need product data, and when I mean local, is that this data that you give when you are dealing with this module. If I'm dealing with a boiler module, I will only give data on this boiler. And typically They are organized as a product description, which is qualitative typically. Just to make an example, a boiler can be condensing, non-condensing, standard boiler, low temperature. And you will see shortly why this is useful. And this may drive, for example, calculation options. If it's condensing, you need a different calculation option. Think about heat pumps. There are several possible combinations of a sink and source and of heat pumping technology. So you need to select the proper, I would say, the proper calculation path and also the proper set of data that will be required. Then you have the actual product technical data, which are quantitative, the power of a boiler, the efficiency of a boiler, and other properties. Then you have system design data, which are describing which are the characteristics of your application case. And typically, again, these are local data. For example, location of boiler. Depending on the location, you have different treatment, for example, of recoverable losses or the hydraulic connection. And you might divide this into further into process design data and control type. Very important also the type of control. Then you have also data about operating condition, which is really the connection with other modules for the calculation and constants. And of course, all these things are reflected in the accompanying Excels, where the data are presented in this order. This is quite useful to know to use properly these Excels. And this is just a simple graphics to show how it's organized. In fact, here you have the operating conditions. So this is the type of data that will connect the module, your module, to the rest of the calculation. And typically here you have your data that are local, which describe your specific item. So typically selection properties, I mean, it's a kind of qualitative data that will help you to which will define which data are really required. And after you filled in this, then so your module will do the calculation and you will get the output data, of course. What's important here is that very often you see there is really tons of data, so it looks like very long to be done. We will just show this shortly here, how to facilitate the input, for example. This is just a list which is awful, a lot of data for just a simple boiler, but actually there are two solutions to facilitate this. Either you have a database, and what could be very useful, and typically this is fulfilled by the software with which you will use any calculation method. Probably you will not input all the data, will just select one make and type of boiler in the archive. Or if you don't have the specific one, you can also use aggregation of data, which is useful to present default data, for example, for national options. Just for example, choosing by an atmospheric boiler, a standard boiler, or a condensing boiler, you might have a whole set of data of product technical data, which is selected in one click based on the typology. This is another way, for example, of simplifying the data input. Coming back a little bit, sorry, because I inverted a couple of slides. The modular structure is also very useful when you have to use alternative methods if you want to nationally have something tailored, because the modular structure means that you have, for example, here a general part. We will have a general part for each service, and typically here you see 15 EN 15316-1, which is a general part for heating and domestic hot water, and here you have all the modules for the paths of the systems. And of course, you have a flow of data, which here is the data for the operating conditions. And here you have a flow of local data, for example, about product or about the configuration of your or location of your equipment. And these are all input to your local module. But if you want to use, local module, in that case, it's quite simple. If you have the same interface, it's easy to integrate a non-EN standard, a national module, until we reach an agreement for a whole calculation scheme. So these are advantages of the modular structure. And where is the problem? The problem is that the connection between modules is not only energy. So in the past, it was all the calculation methods, the national calculation, was EN. It was quite simple. You thought you calculate first needs, then you go for free systems, and you get your delivered energy. So the connection, let's say the path connecting modules, was just dealing with energy. So it was a simple streamline. Now, the connection is also operating temperatures. For example, we dealt in this webinar, for example, with heat pumps, and you notice the sensitivity to temperature of these devices. Then probably you might have several generators, so you have to deal with priorities. There are interaction between building and system in two ways. It's not only building requiring a need, it's also systems losing or dissipating energy and causing, it could be a gain, but it could be also a supplementary load. For example, in summer, so domestic hot water is contributing to your load. So it's a two-way interaction. And even then we are also making connection between systems for various services. So for example, heat recovery from a chiller, you desuperheat to provide domestic hot water. And you have just seen some problems, some examples of interaction between energy needs and ventilation system with just a few possible control options. So now, if we want to have high performance building, this is more and more important. So the real challenge is it's relatively simple to deal with each module, but the real challenge is having them work together smoothly. In webinar 7, we've seen an example of overall calculation, but in fact, there were already some particularity, but it was not the full scale of the possible option. For example, there was only one building zone and not shown. There are some relevant interactions bypass indicated energy flow. So just to say that the real challenge was really this kind of thing. So it's relatively simple to deal with the module, but you have you need to have them working smoothly together, even if you change the configuration of the system. And this was an example. First, for example, calculate domestic hot water needs because they are not influenced. So you go to domestic hot water distribution. You have you go to the generation only for domestic hot water, and then after you have done your heating and cooling needs, you go to the heat pump. So all the boiler and cooling and so on. And you might have the risk of iteration, and as Gerard said, you could also avoid this by using data from the previous hour. So the calculation order is to be carefully designed and to avoid costly iteration in terms of time of computation. So, but all this looks again very complicated, but we shouldn't be afraid, because as I told you, there is a front end and a back end. So the front end is seen by those who actually do the calculation and use the method. And their concern is basically, first of all, describing the configuration of the building and systems. So it means drawing, and there are plenty of user interfaces, two-dimensional, three-dimensional, drawing two-dimensional things that are done 3D to help you, and systems. And typically, for example, you've seen the example before, air handling units, you might have a lot of possible configuration. It's just some selection on drop-down menus to describe and properly input your build. And then, of course, you have to input also data about building elements and system components. And here you might have databases or aggregation of data. Describing the operations of building and system usually is not a problem when you are on regulatory purpose, because you are using default operation schedules when you are doing this calculation for legal purpose. You will do something specific just when you are on energy audit or some special calculation. Well, of course, it's important that you understand the calculation and the indicators, and that we cannot avoid understanding what we are doing. And of course, the front end could be quite simple with all the help that are available. Well, so what you've seen mostly here is the back end in this calculation. So this is for those who design the method, write the standard, and their concern is structuring. The most important concern is structuring the modules and their inputs and outputs, so that it's easy to combine them, and it works anyway without consuming too much calculation time if we go hourly. But as you've seen, for example, again in the example before, to see what happens really and to have a correct calculation of when you are dealing with ventilation, air conditioning, you need definitely something which is hourly. So doing this and define the calculation structure to be software proof and easy to adapt, this is the real challenge which is to be won. So the conclusion is, don't be afraid about the impression of complication that might have come out from this webinar. It was just to explain what's behind. And we cannot avoid that modern buildings and systems are more and more various. You have more and more technologies, and there are interactions more and more between building envelope and technical systems. Sometimes even the building envelope is a technical system, if you think about movable shadings and all these kind of things. And since there are small amounts of energy, anything now is relevant. And to go through this, a clear modular structure is required to adapt the calculation. And the challenge is really to define a structure that can connect all these modules and in a lot of ways, so that you can describe correctly your buildings that you are calculating. And most of these difficulties is not seen by the end user, because the flexible structure allows him to describe a large variety of situations. And then you have database and data aggregation. And this concludes my presentation. And there is some time, I think, for questions. Thank you for the attention.
Yes, thank you all. So it's the Q&A session, so please feel free to ask any question in the right box here. So let's start with the first one for Gerard. So why does EN 16798/7 cover both natural and mechanical ventilation? Would it not be more logical to have separate standards for the two?
Yeah, well, thanks for the question. The reason is actually the modular structure. We try to fit this standard in the modular structure in the sense that it covers one of the modules, M5.5, which is ventilation emission. And by emission, we mean that's the determination of the flow rates. I have to say that for the purpose of these example calculations, I realized that this has also disadvantages. What I did is actually I took apart the spreadsheet and made a separate one for the natural and another one for the mechanical calculation part of that standard. So avoiding all the ballast of the other part being involved with the calculation. So yes, there are pros and cons for such decisions, but it has been decided this way, and I tried to rationalize this decision. Is that okay?
Yes, as far as I understood, Gerhard, this concludes your answer. I think it is clear, but we're waiting for the next question.
Yes, okay.
Sorry, I had problems with my microphone. Can you hear me?
Yes, we hear you.
Sorry about that. So I asked the question again. A question for Dick. A bottleneck for using the hourly calculation method is that you need hourly climatic data. How can that be solved?
Yeah, thank you for the question. So Yeah, we got that question several times at earlier events, and luckily we can say that since recently, thanks to work done by the Joint Research Center from the European Commission, there are hourly meteorological data available for almost any location in Europe and outside Europe. And of course, as EPB Center, we are not responsible for the quality of the data, but you can find all the background information of how these data were developed at the Joint Research Center website. They are created conform the European and international standards to create what many of you might be aware of, the typical test reference years. So you just go to the Joint Research Center website, find the typical meteorological years where they have these, where you can generate these hourly data. And very recently, just the last month, we ourselves from the EPB Center, we created a conversion tool to convert the output from this typical meteorological year generator from Joint Research Center into data that can readily be used as input for the EPB standards. And more information can be found, by the way, at the EPB Center website when you go to the Climatic Data standard.
Thank you. Another question, wouldn't a description in a programming language as Python be clearer than using spreadsheets?
Yeah, let me give an answer. Maybe Laurent and Gerard can add to it. So the main advantage for the spreadsheet is that it is easily accessible, that everyone knows how to scroll through a spreadsheet and to read the formula in the cells. And so to fully understand what is being done in the calculation step by step. And of course, if you want to create a tool for practice, then you would go to a real programming language like including the modern ones like Python. But that's a different purpose. So I hope we explained that the spreadsheets have as main purpose for demonstration and validation and showing you all the steps in the calculation, even if it's concerns, like Gerard said, 150 equations for a certain certain standard, then you can still follow the whole process.
Yes, I agree with Dick. The question is that at this stage, you want to demonstrate and validate the calculation procedure. So the Excel is I think the most traceable way of doing a calculation automatically. Of course, it will not be a high performance calculation. It takes time, but you can at any time review and see any calculation step and any detail in your calculation. And by the way, the Excel spreadsheets allow you to check any single calculation step in a single calculation in any single calculation interval, and you can review it easily to find out why things happen and if they work properly. So the issue is that here the goal was documenting, tracing.
Yes, and perhaps I may add to that. The availability of the spreadsheets, we expect that the software developers who really make this software that is user-friendly for the end users, may use those spreadsheets to understand the text of the standards, to interpret it in a correct way, and also to check their programming if it's correct according to the standard.
And
Thank
not
you.
to mention, sorry, and not to mention the fact that everybody has Excel, not everybody has Python.
Yes.
Yes, thank you. Another question. Would member states need now to update the calculation methods developed so far? Please, anyone can reply.
Yeah, I think for you.
Well, could you repeat the question, because I didn't grab it totally.
Would member states need now to update the calculation methods developed so far?
Well, it's a difficult question, because we noticed that in many European countries, member states have, of course, put calculation procedures according to national building regulations in place of the set of EPB standards, by saying, well, these calculation procedures follow those standards for a certain level of accuracy. Some say it's more or less 90% of what is included in the standards. Others say it is perhaps less. But it's very difficult to say that. It's one of the greatest difficulties is that most national procedures are monthly, which includes a lot of assumptions that are a little bit hidden. So yes, if member states, and some member states, I had the impression they're working on it, want to have a fully suitable procedure where you also can allow hourly calculation procedures, they can use the current standards and all the Excel files and additional information we provided the CPB centers to develop a national procedure that is really according to the EPD standards. So some countries are still in the process to do that. So they still keep their more or less old monthly procedure in place with some updates. Other member states have difficulty to do that, to invest in that, and they really welcome support from outside, you could say. But perhaps one of the team members want to add something to this.
No, it's a good answer.
Okay.
Great.
Yes.
So let's go back to the softwares. There is another question. Besides the Excel sheets, are there any calculation softwares available that integrate all the EPB standards in a user-friendly way? If not, is there any developments going on?
So I may try to answer. And of course, this is the question of the chicken and the egg, because developing such a software is a huge work, and so you need also a market, so adopt these standards. Maybe the good news is that we have half a chicken and half an egg, at least, for example, for Italy, where, as Jaap said before, there are some development ongoing, and where we are, there's work ongoing to try to use the EN standard on the hourly basis. So some software companies have developed, for example, the needs based on the 15.2016, but it's until now it's half the egg, because it's only the needs, and then you proceed monthly with the systems. But nevertheless, this is an ongoing process. So I think with some time, you will have this available.
Yes, to add to that, and I agree with Laurent, it is an ongoing process. And when I discuss this question with software developers, they say, because most software developers work in a member state or has a market in one country, they say, yes, we are interested to do so, but as long as our government doesn't accept the use of our perhaps better and more sophisticated software, then we don't see a market. So that's the chicken and egg. So it's I hope that there will be very soon some countries, perhaps like Italy or France or whatever, that will show that the added value of such a dynamic software, also including the systems, the heating, cooling, and ventilation, will be advantage for bringing up innovative solutions for energy performance. Thank you.
Thank you. Okay, let's move on with another question. Can a detailed building simulation tool be used instead of EN ISO 52016/1? Why not use, for instance, Energy Plus?
Okay, that seems to be a question for me, Dick van Dijk. Well, yeah, you could say, why not use Energy Plus or Transys or ESPR? So one of the detailed dynamic building simulation tools. Well, instead of the calculation according to the standard in which I explained that it is tailored to the application. Well, of course, each country is free to set rules in the national building regulations that these tools can be used. But if we want to create a standard which is unambiguous and reproducible and also transparent, then we're looking for a method that is fully described and can be checked at for each equation, for instance, and that's what we try to do in the EN ISO 52016 Part 1, and also that you make sure that the input you need for this calculation method is exactly known what is meant by it, and it's clearly linked to the output of other standards, which may be products or processes, as Laurent explained in his presentation on the modular approach. And also, if you think about the modular approach, so the EN ISO 52016 Part 1 covers only the calculation of energy needs and the indoor temperatures. So that's a limitation compared to most dynamic building simulation tools, where also other services are integrated. But the advantage of the modular approach was already explained by Laurent, and I could also add that to that an advantage of the modular approach is that for each part you have a group of experts that is responsible for the technical content of that module, so of that specific standard. So for instance, the ventilation experts developed the ventilation standards, and heat pump experts developed the heat pump standards. And then you have this overall framework in which they all fit together. And that is a quite different approach compared to dynamic building simulation tools, which are often more black box than compared to this approach that we follow. So I don't know if other panelists want to add to this.
Well, another good point also is continuity in the description of the building, because when you are doing an actual calculation for an energy performance certificate or for compliance check, the most time-consuming task is describing the building. And to have the same type of description, the same data, this is clearly something quite easy. So with 52016, you are using a lot of advantage of hourly calculation with no extra burden for data input.
All right, thank you. So maybe one more question for Laurent. Are product data as reported by manufacturers and or based on CN or ISO product standards direct suitable as input data for the EPB standards?
Well, that's a good question and a topic of discussion currently, because manufacturers, of course, their main concern is selling products, and that's correct. And in the European context, there are two basic directives. There is the ERP and the EPBD. So one is, both are concerned with energy. ERP is saying very shortly, you're not allowed to sell in the European market a product which is not energy efficient as a product. And the EPBD, we are allowed to build only efficient buildings, which include a lot of products. And of course, the perspective of these two standards is quite different, because for the ERP, you are interested in testing all products in the same conditions. So you have a lot of standards and also data products that are intended to mark them as CE marked so that they can be sold. And typically, all are tested in some average condition to get one figure. When we go to EPBD, which is our task here, and now we need to evaluate the products in all possible operating condition, even the wrong ones, because of course you have to show also something which is wrong. So it's not always easy to have the enough data to represent the behavior of the product easily. So it's a topic which is currently needing some discussions, and we have a lot of examples, especially in technical systems of this issue. So we will need some time and some discussion to harmonize these things. Also because ERP also is tailored for, let's say, off-the-shelf products, which is not the case of heating system or a building installation, where you're not just taking a product off the shelf and putting it on the system. There is a design behind, and the design behind is taking into account a lot of more things than just an average value for the product.
Thank you, Laurent. So as there are no more questions, I will close here the Q&A. So I would like to thank all our panelists, the EPB Center and Riva for this long series of webinars. This was the last webinar of the EPB Standard series. However, remember you can rewatch all the past webinars on Build Up in the Learn section, as I told you before. So thank you all again.
And I want to thank Build Up team for their support to accommodate these excellent webinars, and thank all our attendees from the last 10 sessions for their interest and their feedbacks. And we are also happy to answer questions when you assess our webinars on a later date, and we are open for any communication. So we want to serve you as a user of the EPBD standards, and so keep online and look at our website and give us feedback when you have questions. Thank you very much for your attention.